So in the last lecture, we took a look at the need for formal specifications and formal methods in the software engineering processes. And in this lecture, we're going to go a little deeper into the two modes of formal specifications, the algebraic form of formal specifications as well as the model-based specifications. Recall that we started out with trying to specify requirements using natural language, and there were certain disadvantages that came out of this which were quite significant, and we summarized those disadvantages in this slide. The first one was clearly the ambiguity, right? The same statement written in a natural language could be interpreted in multiple ways by multiple developers or multiple analysts, as a result of which what came out of the whole process was not necessarily what was intended by the client doing the specification. The second thing, the problem was the multiple levels of specificity within a single specification. That is, there could be something at a very high level of abstraction, such as the editor that we talked about, the grid editor example that we talked about. At the same time, there could be something with a very detailed, a level of detail that was not commensurate with the earlier parts of the specification. The last disadvantage clearly was one of verbosity, where using natural languages to specify what the software was meant to do was going to result in significantly larger documents than using formal methods. So we saw that there were several types of formal methods, the two main types being the ones that were based on the state of the objects that were being described. We took a look at the library example the last time, and these were called state-based specifications. A family of languages belonging to this was Z, VDM, and so on. And there are also the algebraic specifications, or those that are based on the operations or the operational definitions, and that's what we're going to take a look at today, is get into a little bit of detail as to how to specify software modules using either algebraic specifications or state-based specifications. One of the things that we have to keep in mind is that specifications lead us to a higher level of abstraction than using either natural language or tying ourselves down to a particular implementation or representation early in the cycle. So that's the other advantage that it tends to give us, is that it saves us from the danger of using physical representations in analysis. A good example of over specification is the Y2K problem. And there what happened was that instead of representing a date as an abstract entity, what happened was there was the commitment for the date being having a year field which was specifically represented 2 digits, and that representation of date using 2 digits was used all over the program code. So as a result of which, when the date had to change to 4 digits, the obvious problem followed that there were hundreds to thousands of places in any given program or application that had to be modified, because they all assumed the internal structure of what the date contained. And this was a problem of what is called overspecification. So you're not confining yourself to the interfaces of the entity that you're talking about, the date in this particular case, which should just have been represented as something that contained a year field, and how the year field was implemented, whether it was done using 2 digits, 4 digits, or whatever, should have been completely left out of the specification, but it wasn't. And that the tying into the logical to the physical representation was a problem of over specification. Another problem is that there could be many different implementations that are possible, and each implementation can be tied into the logical representation at a point in time in the design cycle when it makes sense to make the decision, right? So for example, if you consider a stack data structure, which is a pretty commonly used data structure in most applications, the stack data structure can be implemented either using a list, for example. It can be implemented using an array, and so on and so forth. But the decision as to what the representation of the stack is going to be, the physical representation is going to be, and when this gets bound to the logical definition of the stack, should be done as late as possible in the software development life cycle. And again, this is to some extent, it doesn't belong in the specification, but if we assume the internal representations very early on in the cycle, it could lead to several problems. And also the notion of reuse has to be taken into account here, An abstract definition of a data structure such as a stack or a date or the insulin pump example that we saw has to be is something that can be reused over several different projects, for example, or even in the same projects across different modules. But if it is tied to the physical representation that may not be suitable from one module to the next, then the reuse is no longer going to be possible and it's going to get cut off. As a result of which, we need to be moving towards a higher level of abstraction, and that's what the notion of abstract specifications allow us to do. They allow us to view an object, an entity, a module within the specification by its operations and not by the implementation or the representation that it is going to get tied to at some later point of time in the life cycle of the software. So this is also well illustrated by what is called the principle of selfishness. The way it is stated here is that an orange, a fruit orange, can be viewed in many different forms. It can be viewed as a color orange, it can be viewed as a fruit that is going to give some juice to a person who is thirsty. It can be viewed, if you're a painter, it is viewed by the color. If you're a farmer, it is something that you can sell at the market and you can make a profit out of, and so on and so forth. So it depending on the perspective, then a particular logical representation of this can be laid out, and you only want to stick to that particular perspective, and therefore you're moving towards a higher level of abstraction as you go down this path, and that's what we're interested in doing. So before we get into the details of what algebraic specifications consist of, it is useful to take a look at what exactly does a mathematical model of software represent, and we shall look at that first. So the mathematical modeling of software essentially involves translating an input space, which is represented here by I, which is given to a function, and this is the one f that is doing the translation, and this function is translating the input space to some kind of output space, right. So a program is in a sense a mathematical object, and we can write f of I equals O, and the language that is being used here is nothing but a mathematical notation, and therefore we can prove certain properties about it. So it for example, does the software do what it is supposed to do? The second thing is it doing something that it is not supposed to do? Both of these things are things that have to be proved about the software, and a mathematical model will help us create this proof, right. With that, we can take a look at different types of mathematical models, one of which is an algebraic specification that we are going to be looking at shortly. But before that, we can look at something much simpler, which are called I/O assertions. It's a part of algebraic specifications as well, but I/O assertions are much simpler, and I/O assertions simply take the form S P Q. And what this is trying to say is that if S holds before the program P is executed, then Q is going to hold after the program P is executed, right. So an example of an I/O assertion, which is a way of formally modeling software, can be that we have a sum equals 0, that is the preconditional assertion, if you will, and the function that is going to take place, or the software program that is going to run, says for I equals 0 to n, sum equals sum plus ai. So this is the definition of the program that is going to run, and after the program is executed, a certain condition is going to hold true, and that condition in this case is going to be sum equals sigma j equals 1 to n aj. So essentially what we are trying to say is, it is a software specification which says the precondition is that there is a variable whose value is null or equal to 0, and there is a program that is going to execute, and the guarantee that is given by the specification SPQ is that after this particular program executes, which is you're running a loop over a series of numbers which are being added to the sum, then the sum is going to contain the sum total of all the numbers within that particular array, right. That's kind of the assertion that you're making. It's called an IO assertion. It's also another form of software specification that is used fairly commonly. Next, we'll start taking a look at what abstract data types are made of, and what exactly are abstract data types, how do they fit into algebraic specifications. Remember, we said that algebraic specifications focus on the operational interfaces, right, or the notations that are used to lay out the different operations that can be supported by a data type or can be supported by an entity, right. So, for example, a print server is an entity that can support a bunch of operations, and we saw that the interface specification of the print server would go something like it would accept a particular printer to manage, then it would allow you to queue documents to the printer, it would allow you to dequeue documents from the print server queue, it would allow you to monitor the status of the queue at any given point in time, and so on. Right. So, an algebraic specification essentially allows the specification to be decomposed into a set of different objects, and every object is represented by a abstract data type, right. So, there can be, for example, a stack object, it can be a list object, it can be a date object, it can be a Unix directory object, it can be a print server object, and so on and so forth, and every object is represented in the abstract by a what is called an ADT, or an abstract data type, and we will see what the different elements of the ADT are. So the first element of the ADT, as is shown on the slide, are the collection of objects that are characterized by features and axioms, or the type of the object, right. So, for example, if it is a print server, then you will say that the type here is a print server. If it were a stack that you were trying to describe, then you would say that the type of this thing were a stack, and so on and so forth. If it were a list, then it would be a list. So the first thing that the abstract data type consists of is just the definition of the type that you are trying to lay out, and this can be a parameterized type, or it can be a raw type just by itself, right. A raw type is something like a date, for example. It's not parameterized by anything, and it's just a date. However, a list could be a generic list, it could be a list of some specific type of objects only, say a list of integers or a list of rational numbers. In that case, it would be parameterized by a list of some type T, and that type T would be filled in at a later point in time, right. So, it's a set of types that you operate on. The second thing that is important about an abstract data type is the set of operations, the functions that the data type is going to support. Remember, the important thing about algebraic specifications is that it's not based on the state. So, you don't expose the state of the object or the state of the type in the case of algebraic specifications, but it is purely based on the interfaces or the signatures of the functions themselves, based together with the constraints on what these functions are allowed to do on objects of that type, right. So, the operations of the functions are essentially the operations that are applicable to every single instance of the type. And one of the examples here can be that if you take the stack abstract data type, you can push an element onto the stack, right. If you took a look at the date data type, you can create a new instance of the date, you can read the current instance of the date, you can change the month, you can change the year, and so on and so forth. Each one of these essentially represents an operation, and the operation is characterized by a certain signature which says what is the name of the operation, what are the different input parameters that this operation expects or takes, and what are the types of those input parameters, and then what is the output that is returned by the operation, right. There are different types of operations or functions that can exist within the description of an ADT. The creators are those that create new instances of the ADT. So, a new stack, for example, will return a new instance of the stack, a new date will return a new instance of the date, and so on. Then there can be what are called commands. Commands are those operations that change the state of the type, change the state of an instance of the type. So, for example, setting the date or setting the month in a date ADT would be a command function or a command operation. And lastly, we have query operations that are used to extract the state of whatever the data type already contains at any given point in time. Even though even though the state itself is not explicitly being described here, the operations that are possible to manipulate the state in any which way, either change the state or read what the state is, are given out, and the types of the input parameters and the types of the output parameters are also described as part of the operational signature. Right. There can also be partial functions, and these are typically described using constraints or preconditions that we will take a look at later. The third important thing that an ADT contains are a set of rules. It is essentially a set of rules that say that instances of the ADT have to behave in accordance with these set of rules. Right. A good example for the set of rules would be that if you took an empty stack, or if you took a new stack that has just been constructed and you pushed an element x onto the stack, and if you pop the stack, you should get the element x. Right. That is a simple rule that describes the properties about pushing an element. Right. Only those properties that really matter need to be described. It is easy to get carried away when you are describing axioms here, and there are certain laws that govern how many axioms are just right when you are describing an abstract data type representation. And so we need to be careful to stick only to those axioms of properties that really end up mattering. Right. And lastly, remember we talked about partial functions. Functions can be partial in nature, and partial functions essentially means that the function cannot be executed under all conditions. The results of the execution of the function under certain conditions is undefined, that you will not get any result out of it, and preconditions are the way that help us define which functions are partial functions. So popping an empty stack, for example, makes no sense at all. Right. So this here is the example of a partial functions pop, which basically will work only under those conditions that the stack is not empty. Right. And that is an example of a precondition. So pop of a stack would require that not empty of the stack be true, would be a precondition in this particular case. So what we are trying to do here is create intuitive definitions of the stack operations as we go along, or the operations of an ADT as we go along. Right. And what would probably be helpful would be to actually take a look at the entire stack and see how this thing pans out. One of the things that we may ask ourselves when we are trying to do this is, we saw that in the IO assertion type of specification that we saw just a little while ago, we had something like a S P followed by Q, and there the notation was that you had S, you ran the program P, and Q was really the resulting state of the word. So the question we may ask ourselves is, how about the applicability of a post condition to the abstract data type as well? Now, class invariants and post conditions really apply mainly to the operational and not to the operational, the imperative style of programming or style of expression. Right. So those things are not generally expressed in algebraic specifications, because the implication here really is that instead of manipulating an existing structure or an existing instance of the type, you are always handing back a new instance. So the state of the existing type never ever gets changed in this case, and we will take a look at an example of what that means shortly in the case of a stack, and how we write out the specifications of the stack. In fact, maybe it's a good time to go into that right now. What we are going to try and do here is to write down the complete ADT for a stack. And see what the different parts of the ADT look like when it is a stack. Right. So the first part, remember, was the denotation of the type. The type that we are trying to write down here is that of the stack. Right. It can be parameterized by the type G in this case. What we are trying to say is that the stack only takes elements, contains elements of the type G. Right. So that is the only type information that would be needed in this particular case. The next thing that we would have to move on to are the different operations that are going to be possible on the stack. Right. The first operation would be that of being able to create a stack. Let us call it new, or new stack, which would make it clearer. And the new stack is an operation that takes no input parameters and in fact returns a stack. Right. So this notation essentially means that it's something that this notation means that this is the name of the operation, what is being written out, the first part is the name of the operation, followed by a set of input parameters that the operation may or may not take, and that returns what is the type of the return value that is expected. In this case, it returns a stack of type G, right. The next operation, similarly we can write out a bunch of different operations. Intuitively the next one that comes to mind is push, and in the case of push it takes as its input parameters two different arguments. One is an existing stack and one is an element that gets to be pushed onto the stack, right. Taking these two, it essentially returns another stack G to you. Now what this is trying to say, remember this is what we meant by it's the non-imperative or the declarative style of programming in ADTs or this kind of algebraic specifications. Now what this essentially means is that we are not manipulating the same stack, but instead you are returning a new stack which has the element pushed onto it. That is the implication in the signature of the push operation that we have just written out. Similarly, we can write out a pop operation for the stack, which basically takes a stack as an input argument, and what is the pop operation expected to return? Typically it returns back the stack, but with the top element of it removed. So it does not really return the top element of the stack, and we have to be careful of that, which is why we end up writing we end up writing a query operation. Remember the types of operations that can exist. One of them is a creator operation, which is a new stack operation. The push operation and the pop operation are essentially operations that are command operations, and top is an example of a query operation. And top will take a stack and it is expected to return the topmost element of the stack, which is of type G, alright. And the last operation that we can think of that would be useful in the case of a stack is an isEmpty operation, right, which will take a stack, and this is a query against a stack which will simply return a boolean that says whether the stack is empty or not, right. So these 5 operations are intuitively those that can be written out for a stack data type, right. Now remember the ADT is not yet complete, and we need to still write out for the stack ADT, we need to write out 2 more things. Those are preconditions and axioms. So let us just start by writing out the preconditions in the case of a stack, and we saw one of them a little earlier during our discussion. In the case of preconditions, so if you want to look for you cannot pop an empty stack is one of the preconditions, right. So the pop operation has a precondition which is empty returns false. Right. So this is one of the preconditions that would exist in the case of a stack, is that you cannot pop an empty stack. Similarly, if we actually have a if we had a size element that was associated with the stack, then we can also say that you cannot push onto a stack that is already full. But in this particular case, we have really not taken we have really not taken the fact that we have not taken account of the fact that the stack actually has some kind of a pre-built size associated with it. So we are assuming an infinitely large stack, as a result of which the only precondition for this stack is that isEmpty returns false. Now the more interesting aspect of an ADT are really the rules that we talked about, or the axioms. Remember, we said that these are rules that write out constraints on the behavior of the stack. even though we are not actually tying it down to any particular representation, we are still trying to put down certain rules that say that no matter what representation you end up using, suppose the stack is implemented as a list, the stack is implemented as an array, whatever, then you still got to make sure that these rules are valid, and that's what's important about it. So some of the rules that we can start writing down immediately are: is empty of a new stack has to return, is empty of a new stack always have to return true, because as soon as a new stack is constructed and nothing has been pushed onto it, is empty is always got to be true. So that is one of the axioms. And given the precondition, if you do end up popping a new stack, right, so if we apply the pop operation to a new stack, remember we said that the precondition is that is empty is false, but in the new stack case is empty is always going to be true, as a result of which the pop operation always has to result in an error in this case, right. So here are two axioms. The third axiom is that the same thing can apply to top as well. The top of a new stack is going to also result in an error, right. And finally we can write out one rule that basically says that when you create a new stack, and then you push an element G onto the new stack and you take the top of that stack, it always necessarily has to return G, right. What this rule is trying to say is that when you push an element onto a stack that is empty, then there is only going to be one element on the stack and nothing else can exist, and that is defining a property of the push operation per se. And and a way of testing the fact that the push will only push the element once onto the stack, and that element is always going to be at the topmost element of the stack, is to quickly do a top operation on the push of a new stack, which is guaranteed to always return the single element that you just pushed onto the stack, right. So this example is trying to illustrate a very simple higher level of abstraction that we are trying to create out of a stack data type. Now this can be applied to pretty much any module that you end up coming up with in your specification. It could be a date specification that you are trying to write down. So what you are trying to do here is put some constraints on the behavior of what this data type is going to be capable of doing when it is implemented down by the designers and the developers of the system, right. And so this has to be done upfront as much as possible. Now what these axioms essentially help us at the end of the day is that we can do certain algebraic manipulations using these axioms, right. And no matter how long an algebraic manipulation you are given, the rules will always guarantee that you end up with a valid value, right. That is what the rules of the axioms are meant to do. And an example that is shown on this slide, it's a fairly long example. You're taking a stack, you're doing several operations on this. So you're creating a new stack. First thing you're doing is pushing the value x4 onto it, then you're pushing the value x5 onto it, you're popping it, and so on and so forth. It's a huge combination of operations that are being performed on this, and if you work this entire expression out, it is nothing but an expression in the mathematical model that we have created, right. And we can work this out just like in algebraic manipulations. You can reduce certain expressions down to simpler expressions. That's what we can do in this case as well. Given the rules that we have, we can reduce this particular expression down to a single value that eventually comes out of it, which happens to be x4 in this particular case. And what is important is that this single value x4 for this particular expression is going to have to be true no matter how the stack is going to get implemented down the line. And that's what the power of the axioms give us at the end of the day. So it essentially gives us the quality that is unchanging about a stack no matter how it is going to get implemented. So one of the things that we may ask ourselves is that, what about concrete realizations of this? So far we have taken a look at describing a very abstract representation of what a stack data type is, but how are we going to convert this to a programmatic entity that can actually be used in an application, right? And typically there is a very clean mapping between abstract data types and object oriented data structures. This is something that you'll probably see during the later part of the course when we described object oriented design, but object oriented data structures allow us to essentially map these abstract data types very cleanly onto them, and these are called classes, and you must have read about this in a class on object oriented programming. And classes can either be deferred classes, or they're deferred in the sense they're partially implemented, or they can be effective classes or fully implemented classes, right? And depending on how much of concreteness you want to give yourself at a particular point in time, then we can go for a deferred class or an abstract class. So the axioms that we saw on the stack essentially can be very simply stated in English as well, right? I mean, it could have been stated in a natural language, but we chose to write it down in an algebraic specification. For example, one of the axioms was that a new stack is always empty, and we wrote it down in a formal manner saying is empty of new stack is equals true, but that's nothing but a natural language specification that would simply be that a new stack is always empty. And when you push an element onto a new stack, then the top of the stack always has to contain that single element that you have just pushed onto the stack, right? So these things, what you can see is that the mathematical models that we have created using algebraic specifications in this case are a very powerful, concise notation. Remember the characteristics of formal specifications that we talked about last time. One of them was it had to be complete. The second thing was it had to be concise. The third thing was it had to be correct, and there were no ambiguities about it, and so on, right? And those properties, as you can see, are pretty well satisfied by the algebraic specification for a stack that we just wrote out. So we can add certain operators to this. We can add new operations to this whole thing, and what we essentially end up coming up with is a more detailed representation of one of these data structures. So what it takes to get from an ADT or an abstract data type to an effective class is really the specification itself, and this is the unchanging part of it. This can be handed down to a developer, for example, and ask him to implement it, and the developer has to make sure that when he implements it, all the rules that are given in the axioms have to be true. You need some kind of a concrete representation. At the end of the day, when it gets turned into an executable piece of code, then there needs to be a concrete representation, and in the case of the stack, it can be implemented using arrays, it can be implemented using lists, and so on. And what you need now is also a mapping that goes from the abstract data type down to the representational capabilities that exist. So for an array, you can do certain set of manipulations. You have to make sure that for every operation that exists within the abstract data type, you can map it down to the set of operations that are possible in the concrete representation that you have chosen, right? And one of the important things that you have to keep in mind is that this mapping essentially has to obey the axioms, and they have to check for the preconditions that we have laid out in the notation itself. The one important thing that we will discuss pretty soon is the notion of abstract data types and information hiding, right? As you'll recall, information hiding is a very important characteristic of building of software modularization, and what it essentially strives to say is only that part of the data type of the software module that needs to be that is needed for interaction with other modules is the one that needs to be exposed, and details in the internal representation must not be exposed. And ADTs give us a perfect way of doing that, because the ADT part of a data type is the one that will end up getting exposed, right? And that's the public part, if you will, of the module, software module that is being specified, and the secret, the private part that is behind the scenes is really the implementation of it. So, the choice of the representation that is chosen and implementation of the functions by the different features is something that can be deferred to a later point in time, because it is not going to be exposed. Indeed, it can even be changed at any point in time in the program as long as you stick to the specification. That is the power of it. So, now one of the questions that we have to ask ourselves after having just written out the specification for a stack is that, for example, is the specification complete? Right? How can we end up answering the question, what is the reference point for completeness? Right? For a stack, how do we know that no other operations, for example, are going to be required? Right? And so there is the notion of what are called atomic operations and non-atomic operations, and we have to consider implementation to be complete if essentially you have described all the atomic operations. In the case of the stack, we could easily have written another operation called the replace operation. The replace operation would essentially take a stack, it would take an item and it would replace the top item of the stack with the new item that you are giving it. So, mathematically what this would look like is it would be called replace item, let us say, and this would take two arguments. The two arguments that it would end up taking are a given stack and it would take some element G1, right, and this would end up returning a new stack, but the effect of this essentially is to say that if is empty, equals false only if there is an item to be replaced in the stack. In that case, what I am going to do is I am first going to pop the stack that has been given to me, because I have to remove the topmost element of the stack. So, I am going to pop the stack that has been given to me, and I am going to take the result of that pop and then I am going to push the element G1 onto the resulting stack, right. This is the definition of the operation of replace item. However, what we see is that the operation replace item is one that is almost entirely, in fact it is entirely composed of operations that have already been defined. Is empty already exists within the stack definition that we gave, push exists within the stack definition that we gave, and pop also exists within the stack definition that we gave. So, operations such as pop and push and is empty can be considered to be what are called atomic operations, in that they cannot be broken down further and expressed in terms of other operations of the stack, whereas operations such as replace items, and there can be any number of these operations that we can come up with, are what are called non-atomic or compound operations. So, this would be compound in nature, whereas these three would be atomic in nature. So, coming back to the notion of completeness of a specification, what we really have to think about is mathematically if the axioms that have been laid out, right, can be used to prove any expression that can be constructed out of the language of the theory, then it is a complete specification. That is the definition of mathematical completeness, and what this really means to say is that given all the axioms and the operations, if I can combine these pushes and the pops and the is empties and the news and the tops in any particular order, as long as it has to satisfy two criteria. First is syntactically it has to be a well formed operation, right, and semantically secondly it has to be correct. So, what do we mean by this? What we mean is syntactically there are certain rules that we have laid out when we define the operations themselves, right. So, for example, push always took two arguments, which is a stack of type G and an element of type G, right. So, a push of just an element of type G is not a valid operation, is not a well formed expression, in other words, right. First we have to make sure that syntactic correctness exists, and as long as syntactic correctness exists and it is a completely well formed expression, then you have to look at whether the expressions are meaningful. So, for example, do they satisfy the preconditions, right? Some of the operations resulted in an error, for example. So, if there were no errors and if it were syntactically meaningful expression that was being laid out, then the axioms could be used to prove that expression, and that is what we mean by the specification is essentially complete. So, what we are trying to look at is both structural integrity or syntactic correctness as well as semantic integrity that needs to be checked for, and query expressions are obviously very important in this whole operation, right. So, there is a definition of sufficient completeness that is fairly formal that we are looking at this slide, is the ADT specification for any given type, right, is sufficiently complete if and only if the axioms that have been laid out for that particular ADT, right, make it possible to solve the following problems in any well formed expression of E. First, determine whether E is correct, right. Given some expression E and we saw an expression that was the long sequences of pushes and pops on an empty stack which evaluated to this value x4, right. If we can prove that that indeed is the case by using reduction, having used the different axioms that are present, right, and we can prove that value is equal to x4, then it is a valid expression and E is correct, right. That is what we mean by to prove that E is correct. And the second condition that we are holding true in this case is if E is a query expression. Remember, the different types of expressions that can exist are command operations or command expressions, query expressions and so on, and constructor expressions. If it is a query expression and has shown to be correct under the S1 rule that we just laid out, then we should be able to express the value of the expression in a way that does not involve the type T itself that is being tested for completeness. Now, although this seems a little complex, what this is really going to show is the fact that if given any expression that can be formulated out of the language, right. So, the language that is being given to us is a set of operations that are possible on the stack, right, and so replace item, for example, that we just wrote out a few minutes ago is a new expression that we wrote out using the operations that were given to us earlier, right. We have to determine whether this expression is correct or wrong, that is, it is syntactically correct, it is structurally there is structural integrity within this, that there are no error conditions that can exist on this expression, and if so, it is if it is a query expression particularly, then it can be evaluated into a form that does not involve any more operations within the definition itself. So, that is the definition of sufficient completeness. And in the case, there is one other property that we have to look for when we are writing out abstract data types, right, and the other property is that of consistency. Remember, we said that formal specifications have certain properties attached to them. There was one of completeness and one of consistency, and so in this case the consistency rule that can be applied is that any expression that can be formed and is evaluated, there is no two values that can result from that particular expression. So, the axioms that have been written out for a particular abstract data type will make it possible to infer at most a single value for the expression, in the sense that there is no ambiguity that can result from this, as a result of which there is a consistent set of specifications. So, that is the rule here. We will take a look at a couple of other examples so that the concepts become a little clearer in this case, and one of the first examples we will look at is that of a Unix directory, right, fairly common, and this can be applied even to a Windows directory, except that we are using some syntax that is specific to Unix directories, right. So, in the case of the type, it is that of the Unix directory. So, we are not going to go and we will call the Unix directory in a short form notation, we will call it udir, right. Now, what are the different operations that can be performed in the case of a Unix directory? This is what we have to ask ourselves, right. We should be able to go to the root of the entire file system. So, we will call a slash operation which will essentially give you back what the root is, right. The second operation would be that you are able to form a new directory, and this is commonly called mkdir in several Unix shells. So this takes two things: a U directory, that is the present working directory that you are already in, and the name of the directory. So the cross essentially means that it is a Cartesian product here. The name of the directory, which is simply a string and gives you back another Unix directory, right. Now cd, which is the change directory command, which is also used quite frequently, takes where you are, which is the Unix directory that you are in at this point in time, and it takes a ID to go to, right. It can be an entire path that you are giving it, and then it returns ID or a name is actually being used interchangeably. So I am just going to write that down here so that there is no confusion. They are both strings. A path is nothing but a string as well. Equals string. So the cd operation takes a Unix directory and the directory to which you want to go to, and it lands you in that particular directory itself, right. Now what are the other operations that can be formed in the Unix directory? One of them is pwd, or present working directory, which basically takes a directory as an argument and returns you back the ID or the name of the directory in the form of a string, right. All the way from the root, it is going to give you the path to the current working directory that you are at. Now you can, these are the basic operations. One more basic operation that you can think of that might be useful is to determine whether a given directory exists on this file system. So you can say that here is an ID, search the entire file system for me and return me a boolean to say whether this is indeed a directory that exists within this file system. So we have written out a few operations that we believe are atomic operations in this particular case, and what we have to look at next is the notion of writing out the different we have to look at the notion of writing out the different axioms, because that is what is important to us. Right. So what are the axioms that can be applied to the different operations that we have? So right, we had a couple of PWD operations. We can think of axioms relating to PWD. So PWD of slash, right, will always be the string slash. So for example, if this is a root directory that you are in and then you ask for the present working directory in the root directory, it always has to give you back the string slash, right. Now pwd of make dir command, and make dir command takes two arguments, which is some directory and some ID, right. So this is assuming that equals pwd of d itself. Why? What is this axiom trying to say? This axiom is trying to point out that the present working directory operation that is applied to a make directory operation of d and I, right. That means you are in d and you are making a new directory whose ID is I, then it is the same as applying the pwd operation to d, because you are not going to end up changing the directory in that particular instance, right. So that is nothing but d. Similarly, we can apply the pwd operation to the change directory structure as well, and then change directory also takes two arguments. Remember, it takes d and I as the two arguments. You are changing from the directory d into the directory I, and here we can say that the result of this change directory operation and pwd is nothing but the pwd of I, because you are changing into the directory I, right. So that is the result of this particular operation. Similarly, we can write out a set of other axioms that will essentially give us some correctness criteria on the Unix directory structure that we just wrote out on the last slide. Just for reference, I am just reproducing this one, and it looks like we had all the operations. One of the other operations that we can choose to define, for example, is the notion of an up operation, right? It's like instead of saying cd dot dot, which is what you normally end up trying to do in the case of a Unix directory, you can define an up operation which basically takes you up one level in the directory hierarchy, right? And no matter how many times you go up from the root, you always have to be in the root would be an axiom that you would also end up considering writing down in this case. One more example that we would like to take a look at before we close this session on algebraic data types would be the case of a list. Again, a commonly used data structure, and let's first write out the operations. The type is fairly obvious. The type is list of G. This is a parameterized type. As you can see, the Unix directory was not a parameterized type. In this case, it is a parameterized type. The different operations or the functions that can be used to manipulate instances of the of type G, type list of G, is first thing you should be able to create a list or a make new list kind of operation, and this takes no arguments and gives you back an item of type list of G, right. Now here we have the notion of an insert on a list, right. The insert takes a few arguments. It takes a list, it takes an index at which to, so the notion of an insert being different from the notion of an append, it takes a particular index as to where this thing is being inserted, and it takes the item, right, G itself, the item to be inserted within the list, and it returns another list of type G, right. Similarly, we can have a delete, and delete will take a list as an argument and an index as to which item do you want to delete, and this returns a new list, right. Now you can also have a retrieve operation, and the retrieve operation taking a list and an index, and it returns an element of type G. Similarly, you can have an is empty check, just like we had on the case of a stack, and is empty takes a list and it simply returns a boolean to show whether this list has any elements within it or not, right. Now the one thing that is left for us is to write out the axioms for the list, and the axioms for the list, there are many axioms that you can end up writing for this, right. You can write based on the one of the operations that we missed out in the case of a list is to have an operation that will return the length of the list, right. So the length of the list will take a list as an argument, and it returns an integer which denotes the length of the list, right. That was one operation that we missed out, so I am just writing it on top of the slide in this case. So some of the axioms that we can write out are things like, when we create a new list, is empty of a create is indeed true. Similarly, we can say is empty of a create followed by an insert create comma G1 is false. What this is trying to say is that if I have an empty list, I have just created it, I'm checking the query operator is empty on a newly created list, it has to return true, whereas the is empty operator on a list that has been just created but an element has been inserted into it is false, and so on. So these are the kinds of axioms that we would end up writing even for the list, just like we had written for a stack, and there are several axioms we can write. We have to create combinations of the operators in order to write down the axioms, and there are certain rules for that as well that we won't go into because of the complexity of some of the rules, but the definition for completeness that we had followed earlier and as well as consistency are two things that we have to be able to prove at the end of the day, having written out an abstract data type specification. So what we've looked at and what we have seen in this class is some ways of actually translating the notion of a formal writing down a formal specification in the first place. What does it look like? What are the different structural elements of a formal specification? And we have written that using algebraic data types essentially. We haven't gone into state based models, Z, VDM and so forth, but these are some things for which references will be available as part of this course, and you can choose to look them up. So what we have done is we have seen how to write out algebraic specifications, how these can be formal in the sense of creating mathematical models which we can use to prove the correctness about the language that we have just ended up creating, and hopefully these methods will be useful in further specification efforts that you may be involved in.